Hello and good afternoon. Welcome, as promised, to part 2 of Seeing the Bigger Structure, mathematics version of seeing the forest for the trees, and not getting caught up in the finer details, but noticing first and foremost the bigger idea, what is going on with these functions, specifically when they start being composited together and you get these large beasts, and noticing first and foremost, don't start at reading x squared, but say, wait, this parentheses, okay, then divided, it's a thing divided by another thing that's a rational function first and foremost. That is the goal. And to reiterate, in order to reach that goal, you first have to master these sub-skills. You must understand function notation in order to read those more detailed versions. And it's also very important that you understand function definitions here. And that's what we're going to focus on today, how that contributes, why it's so important, and the two sub-skills of getting a good function definition is relations and sets. So let's skip over to here, part 2, function definitions. So we're going to start with sets, okay? And sets are should be the more natural expansion after you learn your arithmetic. Like, here are the numbers, here you add and subtract them, and here is how you can group them together to create new unique things called sets. Okay? And all of arithmetic and algebra is actually manipulations of sets. If you dig into their definitional features, a lot of them will go back to rules for dealing with sets. And sets are just groups of things, just a collection of stuff. Okay? Sometimes they are the same thing. Sometimes they have a shared property, all of the even numbers or all of the integers. But you can put together your own set. You can just make a bin. Here's a set. I'm going to call it Bob. And inside I'm going to put a 2, a 3, a 7, and the color blue. Okay? Right? It's just math putting its toys into labeled bins. Right? Because sets have, of course, names, and they have their contents, whatever that is. Similar to a variable, but a variable has one contents at a time. A set can have any number of contents. And along with sets comes set builder notation. Okay, probably the best notation. Honestly, you should get used to using this instead of interval notation. Interval is so limited. Set builder can do so many more powerful things. This is the one with the braces. Okay. And sometimes you'll see this vertical bar in the middle of it, and you read that as such that. Again, mathematicians and their shortcuts. We're as lazy as possible. We've turned every possible word and phrase into a single symbol. And then you get this guy, which is not really an E. It's not even a Greek epsilon. It means is an element of, the symbol for element. And so this example here would be, to a mathematician, says 5 is an element of a set called Z, where Z is the set of all things X such that X is an integer. Okay? That's all that means. There's a few more things that make sets stand out as a useful tool and a useful foundation for a lot of this algebra. First is that flexibility. The set itself can contain a finite or an infinite number of items. And you can write them out as a list. So you can write down everything inside of the set, which will take you a while if it's an infinite set. But here you have, milk, eggs, and fabric softener all inside the set. It's a set with 3 items in it. Or you can write them as a rule. So here's the set that contains Kevin's shopping list. Or rather, you'd want the set contains the items on Kevin's shopping. So better would be the set of all X such that, right, vertical line, such that X is on Kevin's shopping list. Okay? And that would also clue you into, this is a set that contains these 3 items. Right? And yeah, in case it wasn't obvious, the set can have more than just numbers. In fact, sets can, I'm going to skip my own ordering here. Sets can contain nothing at all, and you can call it the empty set. Okay? Or a set can contain more sets. That's kind of funny to think about. And also, sets can have an order to them. Maybe it's important that the milk comes before the eggs. Okay, a recipe might be considered a set. You know, add these things to the pot in this order. Okay, that can be there. And at this point, I'm gonna just bring up this reminder again. Seriously, just learn some programming. Okay, find a book or a website. There's several of them out there. They're all great. I recommend Python. It's super easy and quick. But programming is going to force you to get used to dealing with sets, ordered sets, arrays, functions, defining functions, variables, setting up variables, iterating on variables. All of that good stuff just forces you to think logically and work with very, very specifically defined mathematical rules. That's just algebra. Okay. If you want to know more about sets, here are some excellent resources. Math is Fun has a great introduction to sets. This is a nice short little article to read. Along with that, they have a really good summary table of all of the elements in the set, and all of the symbols that go along with that. Let me just click and open that thing, right? So all the common symbols used in set theory, and all of them that you might, we don't use a lot of these in the middle for algebra, but it's a really handy reference for what all of these things mean when they show up. Okay, and tutorials point. This is from discrete mathematics, a whole nother realm of mathematics that deals specifically with sets and combining them, as opposed to algebra, which is dealing with continuous quantities, right? You have 1, 2, and all of the fractions in between. Discrete mathematics is no fractions. So if you don't like fractions, discrete math is the way to go. But it gives you an excellent rundown of the different sets and the type of sets and the special names for the unique sets, similar to that table there. So that's another good resource there. Center of Math is a nice short video tutorial here. I can skip the ads. Okay, and she does a really good job setting this up. This is from you can see there's a continuation here with sets and subsets. This is part of a college algebra course introduction here, so that's a good, nice short video. And Brandon Foltz has a more in-depth video. It's a little bit longer here, so you're looking at like 23 minutes dealing with an introduction to finite math. And just scroll down so you can see the title there. All right, which again is another specific branch of mathematics, but this is a really good detailed lesson here with great visual aids. So I highly recommend that one. Okay, once you've got sets down, now we can go on to relations. Because functions are, as you've probably heard before, it's just a special type of relation. We'll get to that definition in a moment. But the relation themselves are connecting two things, as a relation does in everyday life. Okay, a relationship between two people, right? A relationship between object and sitting on the ground, and prepositions and all that stuff. But in math, we're dealing with connections between sets. And so you can think of a relation as the rule that establishes that connection. The mapping is another term used. It maps one set onto another set. It directs you. You follow the map. It's guidelines how to go from one place to another, how to get from this set to that set. Okay? But the true definition specifically is that the relation itself is a set. And it's the set of ordered pairs. So now instead of just add a little example in here, right? Instead of a set of 1, 2, 3, 4, right? Instead of this, you have a set where everything in it is an ordered pair. So there's an item in the set. And here's the next item in the set, right? So this is the relation. This is why that a table is so useful, as it has your inputs and your outputs, and that table can represent your set, your relation. Okay? Formed by, each ordered pair, of course, takes one item from the first set and one item from the second set. Okay? I really need to highlight this. A relation is not a transformation. it doesn't change one thing into another. It doesn't transform the items from the original set into the other set. They both still exist. I think this is where the function machine analogy kind of breaks down, because we're used to these machines, these factories, to take their input and stamp and mash and crush and paint and whatever, and turn an item into a new item. The old stuff is gone, and the new item now exists. That's not what's happening here. It would be better to say that the relation or the function itself is like the design of a factory. It's the blueprints for the factory, maybe. It's the recipe, because it doesn't take away the old items. It just tells you which items go with which new items. And as always, if you want more, then I would start with a nice definition here. This one is a really good grouping here from Math Insight. It's got a little bit of everything there, also dealing with how a function is a type of relation, so it directly connects to where we're going with this. The Wikipedia article, specifically from the Simple English Wikipedia, I think does an excellent job of breaking down everything you might want to know about a relation without digging too deep into the nitty-gritty and all of the well, they say even this one uses too much jargon, but compared to the full Wikipedia article, which is fantastic for math if you're a mathematician and you already understand all of the notation. The Wikipedia articles usually go into great detail, sometimes too much, that someone in high school would be looking for. But this version is really good. Very simple explanation. And then one of my favorite YouTubers, Brian McLogan here, has a great introduction to what a relation is. That's a nice short video. And this one, IMA Videos, gets into what a relation is. It's also relatively short, and he brings up a great analogy, brings it in a real-world analogy to trying to establish how relations work beyond just numbers. All right, and all of that leads us to the function definition itself. Now, you're probably used to the graphical version, testing for functions. Does it pass the vertical line test? Hey, that's just a visual aid for this relation-based definition of a function, which is to say every input, and the inputs here are just items from a set that we've decided to call the domain. I don't know why. That's just the name for that set that we're drawing inputs from. All of our inputs come from a set, and we call it the domain. Every input is assigned exactly one output, and the output is just an item taken from another set, usually called the range, or sometimes the codomain. Okay? Exactly one output. If there's ever more than one output, more than one possible output, it's not a function. Right? This is why functions are so useful in mathematics, and why we use it to apply, right? Applied math, the application, the usefulness of mathematics come from functions being able to describe things and lead us to an absolute certain answer, because they only give us one answer. There's no ambiguity. You will always go from whatever input, okay? No matter the starting value, you can know the exact final value. You can get there. Eventually, it might be a complicated function. It might take you a lot of time if you have to calculate it by hand, but you can be certain of that answer. If there's ever more than one option, if you're in the middle and it's like you have a choice, well, if I do this, I could get a 3 or I could get a 5 out. I'm not sure. Then it wasn't a function to begin with. Okay? This is the critical point there. It's only a function if you can only get one output from it, from whatever input you give it. Now, related to that, you can, of course, take the inverse of a function, and that is running the process in reverse, right? And that will create a new relation that now takes elements from what was the range set and assigns them an element from the domain set. And oftentimes this can be exactly backwards. You just take the ordered pairs of the first one and flip them all around, and you'll get the inverse function. Oh, but the inverse of a function may or may not also be a function, because you can have multiple inputs that lead to the same output. That's fine. What you can't do is have an input lead to multiple outputs. But if it does, or if the reverse is true, if multiple inputs go to one output, then when I reverse that process, I now will break the function rule. And but if you don't break that rule, if your inverse of a function is itself a function, then you can call the original one-to-one. Right? This is one of those advanced phrases that I feel is so explicit. It means exactly what it sounds like. But every one item here gets one item there, and every one item there comes from one item here. Right? It's one directional both ways. I don't know why we don't introduce that sooner. It's such a useful phrase. Right? This would mean that your function passes the vertical line test and a horizontal line test. Okay, so some more resources on functions themselves. Chili Math has a nice, little more colorful introduction there. The story of math is a good short explanation for relations and functions altogether. And Cool Math, of course, has some very good, more fun, flavorful examples of how functions work, operate. And the MathBits notebook, probably the best, most robust one here. And I've linked you to a topical section here, not a single lesson. So there's multiple parts here depending on which aspect of functions you want to get into. We, of course, looked at function notation before, but if you want to look at the equation side of them, domain and range, and then there's the associated practice problems to go with that as well. Videos, Math Antics has a nice, relatively short video that's fairly fun. Look at that introduction, right? How can you not enjoy that one there? And he gets onto all the different types and forms and visuals of a function, right? You've got table form, and you've got... Oops, where'd it go? Come on. Give me the diagram. There you go. Input-output diagrams there. So a very good video. And I really like this one here from Math and Science because it's science. And I'm, of course, biased. Math was invented to do physics and economics, but very robust sampling here using that function notation in action, tables, graphs, the whole shebang, worked out, lots of examples, a little bit longer of a video. All right, why is all this important? Because the true definition never changes. Okay, this is what I need you to know. All of those other versions, all those other thoughts, the function machine, right? Those are shortcuts and analogies, and they can help you gain an initial understanding, but they're eventually going to break down. When things get really hard, when things start to get weird in the upper levels, in the advanced stuff, maybe you can get by Calc 1 with your function machine idea, but you're not going to get much past that, okay? Calc 2 is going to be a lot harder because you start to get to multivariable calculus, other branches of math, linear algebra, differential equations. A lot of STEM is going to require one or the other of those. Any engineers definitely will require differential equations, and thinking of a function as a simple input-output factory is not going to cut it. Okay? So think in terms of sets. Start with that as your basis, your foundation of your function understanding, because that doesn't change. That will always be true. That holds for all applications and all expanded forms and types of functions and such. All right? And then I reached the end of this, putting this presentation together, and I realized I didn't actually talk about the final skill, IDing the function structure itself. That's going to be a whole lesson on its own. And I think what I'm going to do is, there's not enough time left at the end. These skills I feel that I've addressed here, parts 1 and 2, you should already have a familiarity with. You will have seen them at least once already, so it's not too much to ask. But this itself, saying, hey, make this thing front and center and practice it, is probably new. So I'm going to save this one for next semester. I'm sorry to be such a tease with this. Yes, this is the goal. Yes, it would help you if you can get to this, but I would say I would rather you work on the other parts first and just study more directly for your exam here, and we'll get to addressing this one at the beginning of next semester, and we'll use that to start us off. Okay? I hope this has been useful for you. Once again, feel free to email me with any questions or concerns, and enjoy the rest of your day.